a while since I've done a wrap-up video. So I'm gonna go back. This is week 4 wrap-up video. Right now we're in between weeks 8 and 9. So one of the questions you guys had was this one. In top hat, it said 1.38 and capital E 19 molecules of water correspond to how many moles of water? And so to do this one, first of all, I want you guys to recognize that this right here, this 1.38 E 19 is the same thing as this 1.38 times 10 to the 19th, okay? In Top Hat, I can't do this notation in a question. I'm working on it, so I was putting it like this. I think I figured it out now, but back in week 4, I hadn't figured it out yet. So again, we could rewrite the question like this. 1.38 times 10 to the 19 molecules of water corresponds to how many moles of water? And you guys don't trip yourself up too much on the moles. Remember, 1 mole of anything is 6.022 times 10 to the 23 of those things, okay? Just like if a dozen, right? It'd be like the way you could approach a problem like this, whenever you see moles, try replacing it with the word dozen and see how you solve for it, right? 1.38 times 10 to 19 molecules of water corresponds to how many dozens of water, you know? So if you were going to do that, you would say, well, in 1 dozen, there's 12. There'd be 12 molecules of water. So we treat it the same way as a mole. In 1 mole of water, there is 6.022 times 10 to the 23rd molecules of water. Okay, so if we have 1.38 times 10 to the 19 molecules of water, to convert it to moles, we could use this conversion factor. Again, you guys can decide the best how you convert things. Maybe this is not how you like to do conversions. This is what makes sense to me. I find my conversion factor, again, 1 mole of anything has 6.022 times 10 to the 23rd molecules of that thing. And then I put what I want on top and what I'm trying to get rid of on the bottom. So the question is asking for moles. So I need to get rid of those molecules. So 6.022 times 10 to the 23rd molecules is going to go on the bottom. And that 1 mole of water is going to go on top. And again, make sure you can do the math here. So this is 1.38 times 10 to the 19 times 1 and divided by 6.022 times 10 to the 23rd. And we get 2.29 times 10 to the negative 5th moles of water. And again, a note here, you guys, is that it can be really helpful in these types of things is looking at the exponents, okay? If you look at your exponents here, you have 19 and you're dividing by 23. Remember, whenever you divide exponents, it's like you're subtracting them. So that's a quick way to kind of estimate at what order of magnitude your answer should be at. So a lot of times people might multiply here and you might get something times 10 to the 42. You might get something to the 42. And then that would be a indication to you that you were way off and maybe you multiplied instead of divided. So here when you're dividing, you subtract, so 19 minus 23 and you get negative 4. And so it could be either like plus or minus 1 on when you do that. And so we got times 10 to the negative 5 here. So that doesn't mean you're necessarily going to always have the right answer, but it gives you a quick clue as to if you're on the right order of magnitude. Okay, another question you guys had week 4 work was this one. So use a balance equation to calculate the amount of bromine needed to make 4.75 grams of aluminum bromide. And this is our aluminum bromide. Here's the balance equation from the question. This is a really common calculation in chemistry where you got to take something, you're starting with so much grams, or you want to know, I want to make this much of this product, how much reactant do I need? Or I have this much reactant, how much product can I make? And you can imagine that this is a very powerful tool to be able to do this, especially in manufacturing, right? If you're making anything that involves some chemical reaction, you want to know, right? How much product can I make? That's going to be essential to the business. You need to know how much reactants to order, right? How much do you need? So these type of calculations are just so important in chemistry. So in this case, we're starting with grams. So we have 4.75 grams of aluminum bromide. So we start with that. remember that when we can use the balanced chemical equation, but it gives us the molar ratios. So this is 2 moles of aluminum reacts with 3 moles of bromine to give us or produce 2 moles of aluminum bromide. So we got to convert those grams to moles. And whenever you're doing grams to moles or moles to grams, the tool you are going to be using is the periodic table, which will always be provided to you on an exam. Okay. And so you're going to take, you're going to, again, add up all the molar masses for aluminum and then bromide times 3, because there's 3 of them. And you get 266.69, and that's grams per mole. But since I'm trying to get rid of the grams, grams goes on the bottom, moles goes on top. Once I'm at moles of aluminum bromide, I want to know, again, the question's asking how much bromine do I need? So I need to get from moles of aluminum bromide to moles of bromine. And the relationship is given to me in this balanced chemical equation. And so the tool here to get from moles of aluminum bromide to moles of bromine, again, is the balanced chemical equation. So whenever you need to get, like, again, from one reactant or product to another reactant or product, then you're using the balanced chemical equation. That's the tool you're using. But remember, you can only use it if you're in moles. So this ratio here comes from the balanced chemical equation. We have a 3 in front of the bromine, so that's the 3 moles of bromine. That's what we want. We're trying to get rid of moles of aluminum bromide, and that's here. There's a 2 in front, so that's on the bottom. So if I do a little annotation here, you could see from our first calculation, we got rid of the grams. From this calculation, we were at moles of aluminum bromide, but now we're converting to moles of bromide. So now we're at moles of bromide, but we need to get to grams of bromide. So now again, we're going from moles of bromide to grams of bromide. And the tool for that is the periodic table again. So this time grams will go on top, moles will go on bottom, moles of bromine will cancel. And you get, if you take 2 bromines and add them together, you get 159.8 grams. So then you can carry out the math here. 4.75 times 1 times 3 times 159.8 divided by 266.69 divided by 2 and divided by 1. And you get 4.27 grams of bromide. Make sure you know how to do this on your calculator. Some people end up dividing by the first number, the 266.69, but then multiplying by the second number just because they enter it into their calculator funny. So do these types of calculations. Also, if you want to do this in a stepwise fashion, like carry this out in 3 steps, where step 1, you get moles of aluminum bromide, step 2, you get moles of bromide, and then step 3, you get grams of bromide, that's fine. I just did it all in one here. So again, you need to figure out what works for you. The best way to do that is to work problems. You can search for more problems on the internet if you need more. Come to office hours, go to tutoring. So those are all great ways to practice these types of problems. Okay. Okay. All right, so another question you guys had was how much heat does a 255 gram, aluminum pot gain as its temperature changes from 21 degrees C to 93 degrees C? So these can be a little tricky, but in this section we were talking about heat and temperature changes and phase changes. Notice that this question has a temperature change. Therefore, this is the equation we will be using, the one with a temperature change in it. This delta, this triangle tells you change in temperature. And whenever you see that delta, that triangle T right here, you always, and it's not just with temperature, with anything, this could be a change in volume or anything, it's always the final minus the initial. And the reason I'm emphasizing that is because sometimes you end up with a negative degree change, and that's going to affect whether your heat is positive or negative. So if you always just know it's final minus initial, then you'll always have it straight. So in here, the aluminum pot went from 21 degrees, so that's where it started, that's its initial, went from there to 93 degrees. So it ended there, that's the final. So to figure out our temperature change, it'd be 93 degrees Celsius minus 21 degrees Celsius, so we get 72 degrees Celsius. So to calculate our heat, we got to plug in here. Remember, M is for mass, C is a specific heat, and delta T is our change in temperature. So we got our mass. That's pretty straightforward. That's 255 grams. And then our specific heat we got to get from a table. So I will provide these for you. You do not have to memorize these numbers. We do want to make sure we are using the correct numbers. So in this case, we're talking about aluminum. That's the bottom one here. And it's not the bottom on the top hat. I cut off the rest just for the purpose of this talk. But so here's aluminum. Make sure, again, you're paying attention to which, these are both specific heats, they just have different units. So the middle columns has joules per gram per degree Celsius, and specific heat has calories per gram degree Celsius. And again, just kind of pay attention. So joules is pretty common, but I did it in calories. So 0.215 is a specific heat we'll use. So we end up with the mass 255 grams times the specific heat, 0.215 calories, again, per gram degree Celsius times the temperature change, 72 degrees Celsius. And let's see. So if I do that, my grams cancels here and my degrees Celsius cancels here. And I'm left with a unit of calories, which is a unit of heat. So that's good. Energy. So I end up with 3,947 calories. Notice I only have 2 SIGs max for my question. So I change that to 3,900 calories. And I can change this to 3.9 kilocalories just by adding that prefix of a little k, okay? I divide this by 1,000 to get it to kilocalories, which is a more common unit. Okay. Okay. So this was another question. So kind of similar to the last one, right? Calculate the amount of heat gained by the tissues of a person burned by steam if 5.0 grams of steam condenses during contact. Notice that this was a phase change only, right? We're going from steam and it's condensing, meaning it's going back to a liquid. Again, it's happening on someone's maybe arm or something. But there's no temperature change. This is a phase change only. And therefore, we want to use these equations here. Oh, my mouse keeps disappearing. Okay, here it is. All right. We want to use one of these equations. This either M times delta H of fusion or M times delta H of vaporization. Now, this is going to depend on whether or not we are going from a solid to a liquid. Then we use the heat of fusion. And if we're going from, or again, solid, liquid, or liquid to solid, and then from a liquid to a gas or a gas to a liquid, we use the heat of vaporization. So you got to, again, be able to choose that. And then just make sure we're using the right one. So here we would go back down to our table and we look at water. And in this case, it's not going to matter if it's ice, water, or steam, because again, we're looking at that heat of vaporization. And so for water, the heat of vaporization is here in this right column. It's 540 calories per gram. So all you got to do is just take the mass, which is 5 grams, times that heat of vaporization, 540 calories per gram, multiply it, and we get 2,700 calories. Again, we can divide by 1,000 to switch it to kilocalories, and we get 2.7 kilocalories. Okay. Okay, so I gave you a question on there that asked you to classify a bond. And it was a hydrogen bond, but dipole was also an option. And so several of you commented how a hydrogen bond is a dipole bond. That is true, okay? But you always want to classify bonds by the strongest bond, the strongest intermolecular interaction, because that's going to have the greatest effect on the physical properties of that substance. So again, if you guys remember, dipole is again just attraction between oppositely charged ends of a polar molecule. So they're not ionic, they're not split, but there's an unequal sharing of electrons going on here. So one side ends up with a partial negative charge and the other ends up with a partial positive charge. That partial positive end is attracted to the partial negative end of another molecule, okay? So a hydrogen bond can be thought of as a super dipole-dipole interaction, okay? And so if there are H bonds present, you always classify the bond as a H bond. An H bond is hydrogen bond, okay? So it's stronger, it has more effect on how that substance is gonna act, and so it takes a higher priority, okay? So if it's always a choice between a hydrogen bond and a dipole-dipole, and it is in fact a hydrogen bond, pick hydrogen bond. Okay, and then this was a question about gas laws. So the question was, what is the volume in liters of 1.45 moles of N2 gas at 298 Kelvin and 3.995 ATM? This is a straightforward gas law, ideal gas law problem. So the equation is PV equals nRT. You will always be provided with R on an exam. So R is equal to 0.0821 liters ATM per mole Kelvin. You want to make sure that all your variables from the question are in these units. So they are in this case. So like your pressure is 3.995 ATM. So you got to be able to recognize that ATM is a unit of pressure. I could give you millimeters mercury, I could give you torr, and then you'd have to convert it to ATM, which is a great way to kind of question you guys. The question's asking for volume, so we don't know that. Remember, little n is the number of moles. So in this case, it's 1.45 moles. Temperature is already given in Kelvin, so it's 298 Kelvin. So if I take my ideal gas law PV equals nRT and isolate V, so I'm just going to divide both sides by P, so I get V by itself. I get V is equal to N times R times T divided by P. And if I do that, 1.45 moles times 0.0821 liters ATM, mole Kelvin, times 298 Kelvin, multiply all that, divided by 3.995 ATM. I get a volume of 8.87. Maybe some of you got 8.88. It's close enough. Liters, and that's my volume.